In this lecture, we are going to consider second order partial differential equations linear, which are identified as elliptic equations, and try to obtain a canonical form for the same. Recall, we have seen this example, one example of an elliptic equation, namely the Laplace equation. So, the canonical form for an elliptic equation, we would like to resemble this. If you observe here in this equation, uxy does not appear and uxx and uy appear with coefficients 1. So, this is going to be the model for us for an equation of elliptic type. So, let us consider this second order linear equation 2L, which is elliptic, assumed to be elliptic in a region omega. Assume further that the coefficients ABC are real analytic functions. This is a requirement for the proof of our theorem. In the examples that you want to do, you may simply follow the procedure, you will still be successful. So, let x naught y naught belongs to omega. Now, there is an open set containing the point x0 y0 and a change of coordinates such that the 2L gets transformed into this equation. Observe this part where the second order partial derivatives appear, w xi xi plus w eta eta, it looks like uxx plus uyy and no mixed partial derivative, w xi eta does not appear in this equation. So, this is what is called a canonical form for elliptic equations. So, equation is given to be elliptic, it means b square minus ac is negative, less than 0 on omega. Since the equation is elliptic, we cannot have a to be 0, a of x0 y0, if it is 0, what we have is b square strictly less than 0 is not correct, because b square is always greater than or equal to 0, square of a real number is always greater than or equal to 0. Therefore, necessarily a should be non-zero, and of course, c also cannot be 0 for the same reason. So, neither a nor c can be 0 at the point x naught, at any point in omega, in particular at x naught y naught. And we are assuming they are real analytic, definitely continuous. So, by continuity of the function a will be not 0 in some open set U which contains x0 y0 by continuity. Recall the change of variables xi eta are given by two functions phi and psi. If this gives rise to change of variables, you can invert back x and y, you can write in terms of xi eta, we use capital phi and capital psi for that, and a function of xy can be identified with a function of xi eta, and they satisfy these two relations. And the 2L equation, second order linear equation, gets transformed to this equation, where the coefficients a, b, c alone are listed here, because they are the only things which are important as far as the type of an equation is concerned. So, what do we need for proving the theorem? We want the w xi xi and w eta eta should appear with coefficients 1. In particular, a must be equal to c and equal to 1, and b is 0. Once b is 0 and a equal to c, we can divide with a, then I will get w xi xi plus w eta eta anyway. So, the condition is a equal to c and b equal to 0, that is enough. So, a equal to c, this is a and this is c. So, a equal to c means this equation must be satisfied, and b equal to 0 means this equation is satisfied. The system of equations for finding phi and psi, a remark on that, recall that in the hyperbolic case, when we want to find phi and psi, the equations were decoupled, right, they were decoupled, phi and psi could be solved separately. In the parabolic case, they are weakly coupled, the equations for phi and psi are weakly coupled, in the sense that the equation for phi did not involve psi at all. Unfortunately, once we solve for phi and when we go and substitute in the second equation, the equation reduces to the identity 0 equal to 0. Maybe it is a good thing, because now we can choose psi arbitrarily as long as the Jacobian of phi and psi is non-zero. This can also be explained in following way. Once you solve for phi, which is a solution of the equation A of xi comma eta equal to 0, we need not even solve for b xi eta equal to 0, because it is automatically satisfied by the invariance of the classification type under change of coordinates. Not only that, it is satisfied by any function psi. B of xi eta equal to 0 is satisfied by any function psi. Therefore, we had lots of freedom in choosing psi. The only requirement was that the Jacobian of phi and psi is non-zero. Okay. But for elliptic equation, what is happening? Here also you have phi and psi mixed, here also you have phi and psi mixed. Therefore, it is a strongly coupled system for phi and psi of first order nonlinear PDEs. We can overcome this difficulty by using the assumption of the real analyticity of ABC and some complex variable techniques. You will see that a crucial part of the proof we will skip, we will not do the proof. Okay. This system may be rewritten as this, right. The first equation, I simply transfer psi, all these terms to the left hand side, and I take A common, so that I get phi x square psi x square, 2b common, so that I get phi x phi y minus psi x psi y, and c common, so that phi y square minus psi y square. It is exactly the same equation rewritten. Second equation I am just multiplying with I because I have some idea what I want to do in the next slide, that is why I put I. Otherwise the same equation I multiplied with I. It tells us that some complex things are going to enter. So, define a complex valued function capital phi by small phi of xy plus I psi of xy. So, this system, the system that we want to solve for phi and psi is equivalent to this one single equation now, A phi x square plus 2b phi x phi y plus c phi y square equal to 0. This equation we have seen earlier. This is the same equation that we solved while determining canonical form for hyperbolic equations. Of course, the difference was there that we could factorize as real equations, factors were real, but here it will not happen. It leads to PDEs with complex coefficients given by this equation and this equation. In the case of hyperbolic equation, there was no I first of all, and inside thing was b square minus ac. So, these are the two equations we have. Now, a fact, the system of equations has solutions near x0 y0. This is where ABC or real analytic functions is used. This we can observe if phi is a solution of the first equation. Okay. Remember A, B, C, they are all real valued functions. Therefore, if phi is a solution of the first equation, phi bar, the conjugate of phi, that let us call it is capital psi, that is a solution to the second equation. Therefore, it is enough to solve one equation. Essentially, there is only one equation, right, but that will give us what we want, because the phi is proposed as small phi plus I times psi. So, you can identify a real part and imaginary part, and hopefully that forms a coordinate system, that defines a coordinate system. Therefore, phi and psi are constant on the two complex characteristics. These are right hand side is a complex valued function. Okay. We have not studied in our Picard's theorem how to solve such equations. Okay. This is where it is important that we use our hypothesis and show that solutions exist. Define small phi of xy equal to real part of capital phi, small, because we have obtained phi after this, right. This phi exists is what somebody told us, this fact. So, I have phi and then real part I will call as small phi and imaginary part I call psi. And this defines a coordinate transformation near the point that is left as an exercise, very easy, and the transformed equation has the required form because we made what we want, right, A equal to C and B equal to 0. So, therefore, we will get this. If you want to see a detailed proof, please look at this book by P.R. Garabedian on partial differential equations, you will find full details. Let us solve an example. Here you see we do not care whether it is analytic or not. Of course, here these functions, here it is a constant function 1, here it is 1 plus y square whole square, it is a polynomial, here also it is a polynomial. Of course, it does not matter, we are worried only about coefficients of uxx, uyy and uxy. So, b square minus ac is negative, strictly less than 0 at every point. Therefore, the equation is of elliptic type everywhere in the plane R2. So, let us transform now the given equation into its a canonical form. So, we need to solve these ODEs dy by dx equal to plus or minus I into 1 plus y square. So, we need to solve this ODE I times this because minus I times does not matter, it will be the conjugate. So, this solution is given by tan inverse y minus Ix equal to constant. Okay, please accept this, that this is a solution. Okay. And then real part is x, imaginary part is tan inverse y or vice versa. Here of course, if this is constant I can multiply this with I also again, right. So, therefore, it does not matter what I call the variables phi and psi. In the theorem that we presented, this was called phi and this was called psi, but we are interchanging here. It does not matter because there is no preference for the variable x or y or xi or eta. So, therefore, we propose u of x y equal to this w of x comma tan inverse y, differentiate ux is x appears only here. So, it is w xi and derivative of x is 1, uy will be w eta and derivative of this is 1 by 1 plus y square. So, you can continue like that, compute the derivatives, go back and substitute in the given equation, we get this. So, that is a canonical form of the given PDE. So, summarizing what we did is that we have presented a method to reduce a second order linear PDE which is of elliptic type to its canonical form. We have of course assumed very high assumptions on the coefficients ABC, but you may generally, if you are given a partial differential equation of elliptic type, you want to find its canonical form, you may simply follow the procedure, do not bother about the hypothesis checking for the theorem, and you will still be successful if you are able to solve the ODEs which are coming on the way. And we have seen the method is successfully implemented in the example. Thank you.